All right, sorry for the interruption, but we'll finish the slides in this video. Okay, I'll share my slides with you. And here we go. We're just going to pick up where we left off before. So we were talking about solvent leveling, and we hadn't quite gotten to the description. So solvent with a large autoprotolysis constant can be used to discriminate between a wide range of acids and bases. So, well, why would we want to do that? Well, an acid that is stronger than hydronium ion in water donates a proton to water to form hydronium ion. And remember that equilibrium is reached very rapidly in Bronsted-Lowry type acid-base systems. So what that means is that the strength of an acid is limited by the basicity of the solvent. In other words, any acid stronger than hydronium ion reacts with water, hydronium ion, very quickly. And that means that no acid stronger than H3O plus exists in water. So as an example, let's take a look at HBr and HI, so hydrobromic and hydroiodic acid in water. So the Kas, if you remember back a few slides, the Ka for hydroiodic acid is listed as 10 to the 11th. The Ka for hydrobromic acid is listed as 10 to the 9th. But actually in water, both rapidly transfer their proton to water to form H3O plus, and they behave very similarly. So they appear to be essentially the same. So because of this, water is said to have a leveling effect because the acidity in solution is essentially the same. The same can be true in other solvents. This isn't only for water. So when ammonia is the solvent, then the strongest acid possible is ammonium ion. And under those conditions, hydrochloric acid and a superacid would have the same acidifying effect. So this solvent leveling or leveling effect controls the acidity of the system. So one thing we can do using different acids, different solvents, is we can use a different solvent other than water to discriminate between the acidity of different. So hydrobromic and hydroiodic acid in water appear the same, for example, but in a different set of solvents, they may be able to be distinguished. So in order to discriminate between these acids, we would need to have a window in effect. So these blue lines represent the effective windows of these different solvents. So as an example, and just to orient you to this is the effective pH range down here on the bottom. And so we want to use the pKa's rather than the Ka's to look at this particular chart. You may see a chart that lists Ka's instead, but the window would have to be very large for that. So which solvents, then the question is, which solvents could be used to differentiate the acidities of hydrochloric and hydrobromic acid? And the pKa's are given. And remember, the P anything is just the negative log of whatever follows. So this is the negative log of the Ka. So we need to find a solvent where 6 and -9 both fall in the blue window that's shown. So -6 to -9 would be down here. And we could use a solvent probably of methanoic acid or hydrofluoric acid to actually be able to tell the difference between hydrochloric and hydrobromic acid based on the acidity. Now let's look at the solvent system definition of acids and bases. So I know that you can read these, but I'll just read these so that we keep on the right to the definition. Any solute that increases the concentration of the cation that's generated by the autoionization of the solvent is called an acid. And conversely, for the base, it's any solute that increases the concentration of the anion that's called the base. So let's look at what that actually means here. First, we're just extending the Bronsted-Lowry definition in this case to apply to compounds that act as acids and bases, but that don't have any protons to transfer. So here's an example. So this bromine trifluoride, that's an aprotic solvent, meaning it doesn't have any hydrogens to transfer. So if we're working in that, then two BrF3s can participate in a reaction where one of the fluorides is transferred from one molecule to the other. So the one that gives up one then is BrF2 plus, and the one that takes that on is BrF4 minus. Aprotic solvent, if we add this compound, which is soluble in this solvent, we want to know whether this is an acid or a base, right? So remember, an acid is something that's going to increase the concentration of this BrF2 plus, and a base would increase the concentration of the BrF4 minus. So take a moment and predict, what do you think will happen? If this compound dissolves in solution and it forms stable ions, do you think it will increase the concentration of the cation or the anion? In this case, it increases the concentration of BrF2 plus, and so this is an acid in this solvent. And it does that through this dissociation. BrF2 plus and AsF6 minus are the products. All right, so there are periodic trends in aqua acid strength. So let's, there are two different classes, and we'll go through both of them. So the strength of aqua acids increase with increasing positive charge on the central metal ion and with decreasing ionic radius. So we can use an ionic model to explain the trend for the S block and the early transition metals, and those are circled here on the diagram. Okay, and a little depiction of what this ionic model would take into effect. Right, so we can actually calculate a parameter that would allow us to make this prediction. So for the other later D block and the P block metals, then a covalent model better explains what is happening, right? So the ionic model is going to be based on charges, and a covalent model is going to be based more on delocalization of charge. So let's look at these three ions and see if we can explain the trend in acidity, right? So aluminum, hexaqua aluminum is the most acidic. This hexaqua iron 3 plus is intermediate, and this hexaqua iron 2 plus is the least acidic of these. And then I'll leave you with this question about mercury, right? So what's different between aluminum and iron in these first two, right? They have the same charge, and these will fit in the ionic model, right? The size of aluminum is smaller than the size of the iron, so it will be a little bit higher charge density. And so that's one way we can explain or rationalize that this is more acidic than the iron. And then let's look at the iron 3 plus versus iron 2 plus. Well, we have different charges here, and so we can use that to rationalize the difference here. The iron 3 plus will be more acidic, and the iron 2 plus will be less acidic because of the difference in charge. So I want to leave you with this one as sort of a puzzle. The acidity of this mercury hexaqua complex is about the same as the aluminum complex. So how can you rationalize that? All right, so let's talk about Lewis acids and bases, and this is one of the most common acid-base definitions that we'll use in inorganic chemistry. So by the Lewis definition, an acid is an electron pair acceptor, and a base is an electron pair donor, and they're often shown by these sort of labels A and B with the 2 dots to represent the electron pair, right? And an example is trimethylbromium boron compound and ammonia can react. Ammonia acts as a base here, just like it does in most other cases, right? Where we have the lone pair, which is going to interact with the boron, and then it forms this adduct here. So the boron compound is the acid, the ammonia is the base, and it forms this adduct, which has what's called a coordinate covalent bond. So the electrons are being shared between these 2 atoms. So let's take a look at these and identify the acids and the bases in this particular case. So BrF3 is going to be acting as the acid, and fluoride ion is acting as the base, and then we're forming this adduct with the bromine in the middle and the fluorides attached to it. A feature to look for on the base in a Lewis acid-base reaction is lone pairs of electrons, which aren't discretely shown here, but as fluoride ion. The acid in this case is a little harder to determine than in some other situations where you have a charged central atom. That would be a good acid. So now let's take a look at this other example. I'll give you a moment to look at it, or you can pause, and then we'll label each of the each of the species. Potassium in this potassium hydride here is the acid, acting as the base, right? And the lone pairs on the oxygen are being donated into the potassium metal here. Adduct then is the potassium hydroxide, and we have production also of hydrogen gas in this case. All right, so we can classify our Lewis acids and bases as being either hard or soft, and this classification system allows us to make some predictions about what reactions will proceed and what products will form in the presence of these Lewis acids and bases. So hard acids tend to bond to hard bases. And hard species are those that are small and highly charged. These are typically electrostatic interactions, meaning that the hard acid and the hard base bond together through attractive forces due to electrostatic interactions. Soft acids then tend to bond with soft bases, and soft species are those that are large and polarizable. Those are low charged or even no charge. And these typically form through those soft acid, soft base interactions, covalent bonds where the electrons are evenly shared. So originally, this hard and soft classification was done through experimental evidence, so actual empirical evidence. And one way that we could do that would be to measure the interactions between these halide ions and the various metals that we're looking at. And so hard acids are going to bond to fluoride, which is smaller and proportionally more highly charged, and iodide to the least. Or soft acids would bond to iodide preferably, ion least preferably. And so you sometimes see charts like this. This happens to be from the Shriver Inorganic book, but that show actual log K values, so equilibrium constants or formation constants for each of these compounds. We don't have to make all these empirical measurements anymore, though. We can examine the data. We can collect this information into tables. We can use the tables that are out there. And we can make predictions based on where things fall. So things that tend to be hard acids are small atoms that have relatively low charges. So hydrogen ion, lithium ion, magnesium and calcium ions, aluminum, and so on. Things that tend to be soft acids are larger and have low charges. So copper and gold, silver ions, for example, mercury and cadmium, which cause biological problems, also fit in the soft category. We can categorize then bases into the hard categories. So fluoride, hydroxide, water is surprisingly, or perhaps not, a hard base. Ammonia, carbonate, some of these other ones. And then soft bases are larger or lower charges. So hydride ion, surprisingly, in this category. Cyanide, carbon monoxide, thiocyanate, and so on. It's unfortunately a borderline category, and to really determine what's going to happen with the borderline cases, we would have to do experiments. But things like iron 2+ fall in this category. Things like bromide ion fall in this category for the bases. All right, so if we want to look at something that will happen, try to make a prediction. So zinc oxide will react with this lithium compound here. And the products are zinc with this organic substituent now, and lithium oxide. So how can we rationalize this reaction? Well, we have zinc oxide, which has a soft or borderline metal with a hard base. And we have lithium, which is a hard acid, and this organic, which is a soft base. So the driving force in this reaction will be to switch so that we have the hard ions bound to each other and the soft acids and bases bound to each other. And so the products then are the zinc, which is soft or borderline, and the organic, and then lithium and oxygen, which are the two hard acid and bases. And this just summarizes that. The reaction actually has an equilibrium constant greater than 1, and so the products are greatly favored over the reactants. So I'll just leave you with this idea about the consequences of hardness and softness, and this neat picture of some quantum dots. Quantum dots can self-assemble under the right conditions, and quantum dots are very small, have very neat properties, including fluorescence. And I'll leave you with this picture and the idea that these form partly through a preference of the reactants for the soft base to bind with the soft acid and the hard acid to bond with the hard base. So if you're interested in quantum dots, they are a really interesting class of materials, and there's a lot of great information with great pictures out there. All right, so even with the interruption, that is it for this week's material. So have a great week, and next week we will continue with more inorganic chemistry. Have a great week.